Good afternoon, everyone. It is my great pleasure to introduce our speaker, Professor Ulrich Stadtmüller. Professor Stadtmüller is a distinguished professor at the University of ULM, where he is a member of the Institute of Number Theory and Probability Theory. Over several decades, he has built an outstanding career and is widely recognized as a leading expert in mathematical statistics, probability theory, and analysis. His research contributions are both deep and diverse. They include significant work in asymptotic statistics and probability theory, particularly in limit theorems and random walk models. He has also made important advances in time series analysis with a focus on non-parametric methods and change point detection. In addition, his work in summability theory and functional analysis has contributed to a better understanding of the convergence behavior of sequence and series. Beyond his research achievement, Professor Stadtmüller has played an important leadership role at the University of ULM, contributing to the development of its Department of Mathematics and Economics. He is also highly regarded for his dedication to teaching and for mentoring many PhD students and young researchers across the international mathematical community. It is therefore a great honor to have him with us today. And please join me in welcoming Professor Ulrich Stadtmüller. And please, you can start.
Well, thank you very much for the very kind introduction. You're exaggerating a little bit. But anyway, it's a great pleasure to be with you in this webinar. And I would like to talk about elephant random walk, mainly about work I did with Alan Good at the University of Uppsala. And I will also talk about some results around our work. There are a lot of papers now in this area. I will not mention everything, but some of the results will be presented. Okay. I will make a short introduction of myself because I think most of you don't know me. I will shortly introduce classical random walks. Then I will introduce elephant random walk and we'll discuss about the work we have done about variations of the memory. I will talk about zeros and level crossings, random walks with stops, and I will give some literature, not all, but some of that which is related to my talk. My name is Ulrich Stadtmüller. Friends or colleagues call me Uli. This is an abbreviation in Germany for Ulrich. And I'm a retired professor from Ulm University. And the first question for you maybe is, whereabout is Ulm? And Ulm is a medium-sized city in between Munich and Stuttgart. You see here Munich. This is the southern part of Germany. Here is Stuttgart. And in between is Ulm. We are here at the River Danube. And it's a quite nice city. It is known for having a Gothic cathedral with the highest church spire in the world. This is not quite true anymore because the Sagrada Familia in Barcelona has now, since 3 months, I think, a little bit higher tower, and it will still increase. But this is a Gothic cathedral, and it's a mighty building. But it has also Ulm has some picturesque sites downtown. You see some old houses at a small river, which is called the Blue, because its offspring nearby has a very blue color when the weather is nice. Ulm University is one of the younger universities in Germany. It was founded in 1967. It has departments in medicine, natural sciences, electrical engineering, computer science, and psychology, and mathematics and management sciences. It is a member of the teams which have won an excellency cluster, and this is in battery research. In general, these are the main research topic of our university. Mathematics is involved in data science. Actually, mathematical methods are important from transferring the data from a data source to some analysis and some things you can learn from it. And there's finance and risk analysis, which is one of the hotspots of our department. But you can see and just read what other fields are of interest in our university. In medicine, it's hematology, oncology, research on trauma, understanding age in neurodegeneration. But there's also in physics, quantum technology, and smart sensing systems, and so on and so on. It's just for your information. Well, if we start to talk about probability theory, this is. Sorry, you have a question?
No. Can you do Control L to put your slides full screen, please? Control L, full screen slides.
Okay. Thank you very much. One of the starting points of probability were the classical random walks, where you have independent random variables with plus minus one, being positive with probability p, and negative with probability 1 minus p. And we denote their partial sums by Sn as usually. And the classical limit theorems, being more than 100 years old, are the strong and weak law of large number, saying Sn divided by n converges to the expectation, 2p minus 1 as n tends to infinity, in probability or almost surely. And we have the central limit theorem as written down here, or more advanced, the law of iterated logarithm for this case. And there's much more. Invariance principle, weak and strong invariance principle, level crossing, zeros, number of zeros, etc., etc. Okay, there are many different situations and models to generalize this simple situation. Maybe random walks in a random environment where the probability to go up and down depends where the walk is just in this moment. Random walks with certain dependent structures. And what I'm talking about belongs to the second case, the elephant random walk, which I will define shortly. And it also belongs to the family of so-called reinforced random walks. For elephant random walk, we have again x1 has values plus or minus 1 with probability p and minus p. But then going on, if we have already defined the first n random variables, x1 up to xn plus 1 is chosen in the following way. You choose randomly one of the random variables which have appeared before, and you took this random variable with probability p and the negative value of this random variable with probability 1 minus p. So the index k here is a random variable being uniformly distributed on the set of integers 1 to n. And this is independent of the sigma algebra of the previous random variables x1 up to xn. And as before, I will denote Sn to be the partial sums. The name comes from the fact that the memory of an elephant is supposed to be very good and long-ranging. And here, the random process depends on the whole past from the beginning on. It's not a Markovian process. It can be as well formulated as an Earn model. If you have, say, after n steps, some red and some white balls in your urn, and then you choose randomly one ball, take it out, and with probability p, you replace the same color, or with probability 1 minus p, you take the other color and put it back again. Well, one of the key properties we use frequently in the following: the conditional expectation of xn plus 1 given the past is you choose one of the random variables, x1 up to xn, with probability 1 over n, with probability p, you take this value, and with probability 1 minus p, you take the negative value. And if you p and you add these things up, you see this is just 2p minus 1 as n divided by n. Hence, we get for the partial sum process the conditional expectation of Sn plus 1, Gn is just some number gamma n times Sn, where gamma n is n plus 2p minus 1 divided by n. So if gamma n would be 1, this would just be the defining equality for martingale. And to deal with martingale we know quite well what to do. But if we define another sequence an, which is just the product of the reciprocal of the gammas, and if you multiply this out, this is just a quotient of gamma functions, we find that we can construct a martingale, which is an times Sn. And this was used by Coletti and et al. And Bersu, but it's an older trick which goes back to a paper of Chris Heidi in 2004. And then we are able to use martingale theory. We should note that an is asymptotically gamma of 2p times n to the 2p minus 1. So some n power which ranges between minus 1 and plus 1 if p is ranging between 0 and 1. So as usually we may write the martingale as a sum of weighted epsilon martingale differences, and we find that the expectation is 0 naturally of epsilon n, and the second moment is 1 minus 2p minus 1 squared Sn divided by n squared. This is less or equal to 1, also the higher powers, but furthermore, we will see Sn to n converges to 0, then essentially the variance is of epsilon n is 1. This implies that the square brackets of Mn is asymptotically is the sum over the AK squared. So it's important how this sum behaves. And if we define this sum by nu n, then we get three different cases, so to say. The first one, for p less than 3 over 4, it behaves like a n power times a constant. If p is equal to 3 over 4, ak squared is 1 over k. Then the sum is pi over 4 times log n, and if p is bigger than 3 over 4, then it converges. And then we can apply well-known results for Mn, and then we can transfer it back to Sn. And then we have the following results, going back to Bersu, as I formulated here. If p is less than 3 over 4, then we have a strong law. This is not the strongest form, Sn divided by n. We can have weaker weights. And Sn divided by square root of n converges to a normal distribution with expectation 0 and 1, and variance 1 over 3 minus 4p. You see, something happens if p is 3 over 4, because then the variance explodes. For p is equal to 3 over 4, we still have a strong law and a central limit theorem, but we need a little bit stronger weighting than in case of p less than 3 over 4. And for p is bigger than 3 over 4, Sn with suitable normalization converges almost surely to a non-generate random variable L. So we have a diffuses scheme if p is less than 3 over 4, because asymptotically we have normal distribution, so things are mixing out. For p is equal to 3 over 4, we have limit case, so to say, and for p bigger than 3 or 4, we are not in a diffusive scheme anymore. So this is different from many other things, for example, from the classical random walk. We can also have law of
May I
iterated
interrupt you?
logarithm.
Sorry, Ulrich.
So,
Can you go
sorry?
back to the previous slide, please? Do we have any information about the limit L in the super diffusive
One
scheme?
knows all moments of L. It cannot be 0, so it's positive. Not no. One knows all moments, but I don't know anything about its distribution.
Okay, thank you. Sorry.
Once I wanted to have,
The distribution is not Gaussian.
it's not Gaussian. No,
Yes.
definitely not. Yeah, and for p less than 3 over 4, we can also have a law of iterated logarithm and more. We can also have an invariance principle and so on and so on. Our starting point of Alan Good and myself, where we actually Alan got some paper to review from people in physics who were dealing with such processes which had some effect in physics. And they were asking what happens for different memories. Is there still such a dichotomy and so on? And so we thought, okay, let us look on different memories. To describe this mathematically, we define a memory set subset In of the numbers from 1 to n, and associated with that the sigma algebras of the random variables xj, j in In. And then we can also calculate easily conditional expectations, but not of Gn. Gn is always the sigma algebra of the whole path, and Fn is of the particular memory we are looking at. And yeah, it's more or less the same calculation as before, but now we are just dealing with the In instead of all the so In is always a set of indices describing the memory in the following. Very simple case, the elephant remembers only the first n random variables. For the simplest case, I assume m is equal to 2. Then asymptotically, Sn divided to n has a 3-point distribution, as written down here. So social probabilities, and it's easy to calculate expectation of Sn divided by n and its variance. And the moments converge, everything is bounded to the moments of the limit distribution.
Then M here does not affect the limit in probability of Sn divided by n. There is no n in the asymptotic.
This is Sn tends to infinity, yes?
There is no n in the asymptotic. M does not affect the limit of Sn divided by n in probability.
No.
In your theorem, there is no m here at right. So
yes, no, this is for m equal 2. This is for m equal 2.
Sorry. Okay.
I wanted to have the simplest case.
Okay.
We can also write a limit theorem with random centering. And then we have a kind of limit theorem, we have a kind of strong law, and we have also a kind of law of iterated logarithm, but with a random variable, with a random limit.
Then the two Gaussian distribution here are independent.
It's just the sum of these two. This is an overlaying of two distributions. So it's p times n with the first variance of x plus 1 minus t 0, 1 of x. So it's just if you add two normal distributions with two weights, you get a new distribution, which is not normal. It has two peaks normally.
Sorry, I have not understand here. The first result A, You have as limit distribution P multiplied by some normal distribution plus 1 minus P multiplied by another normal distribution. These two these two random variables are independent or not?
No. It's informally written. The probability of the left side less or equal to x is the sum of two normal distribution functions at x.
Okay.
You can also discuss a general case. It looks a little bit nasty, but the interesting question is what happens if mn tends to infinity. So we have many first steps where you do remember, but I still assume mn divided by n tends to 0. And then we can still have center limit theorem, but with a different normalization. Sn times squared of mn divided by n converges to some normal distribution. If p is less than 3/4, if p is equal to 3/4, we have again similar relation, but with a different norming. And we have also, if p is bigger than 3/4, there's a misprint here. It should say almost surely to 2p minus 1 times r. If p is equal to 1/2, the random walk we are discussing is the coin tossing, so we get Sn divided by square of n converge to standard normal, and we have also a similar case here. And the question is, what happens if mn divided by n converges to c, where c is not necessarily 0, as I did, but between 0 and 1. And Ulrich and Al-Khwarizmi showed that there is asymptotic normality again, and the variance is, as you can read here, I don't have to repeat this, where the constant rho is c plus 1 minus c times 2p minus 1. This is for p less than 3/4, and for example, the other cases are treated as well. And you can, for example, prove if p is bigger than 3/4, you have again a strong law. And Ulrich again considered a more general case where the partial sum is xk, as xk was just given before, and multiplied by random variables ck, which are independent from the rest, and showed again asymptotic normality. So these results are much better than what we had done. There are also other results. For example, Lowlin and Majumdar and Maulik discussed the case where the original random variable k, which was picking one of the indices 1 to n in the case of full memory, is not uniformly, but has some other distribution. For example, some beta distribution. And there you get again a result for the diffusive case, but the limit for the diffusive case is now depending on beta, where beta is a parameter of the binomial distribution, and binomial distribution, and you get also a special variance depending on beta, and you can also play a little bit with this distribution depending on beta. This distribution for the random variable k fits nicely in the calculations. This is why this special distribution came up. Yeah, more realistic, I think it's the case where the elephant has worse memory, so he remembers only the last few steps. Say, the simplest case, n minus 1 and n, so the last two steps, for example. And then we are in a situation that we have a recurrent Markov chain with finite state space of order 2. And we can simply apply results for Markov chains. So we find that Sn divided by n converges to zero almost surely, and Sn suitably normalized converges to a standard normal distribution where the variance can be calculated. And you can do this for any fixed m steps, so n minus m to n, and you get asymptotic normality. And in a different context, Ben-Ari et al. Proved that the variance should look as written down here. I'm a little bit confused about this formula for the variance, because if m tends to infinity, so we are back in the classical case, the variance doesn't fit to the classical case. So either there's something happening or something is wrong. I don't know. Yeah, that's what I just said. So as m tends to infinity, the variance converges to 1 over 4 times 1 minus p squared, which is not 1 minus 3 minus 2p, which was the case in the classical case. An open question is, and we are just discussing this at the moment, is Rafik and a lady from Iran. What happens if m is equal to mn converging to infinity? I'm pretty sure we have again a normal distribution, but things are much more complicated because one could consider this as a Markov chain with increasing chain length. Now, at the moment, we have no good idea how to tackle that. So this is still an open problem. A different case we were dealing with was if elephant thinks of the first or remembers the first and last step and similar memories. And there, again, for example, in this most simple case, we have again a 2-point limit distribution, and one can also generalize this to more general cases. And with random censoring, we get again asymptotic normality. The larger, to calculate the moments, which is quite helpful tool to get some information about what's going on. Typically, one uses conditional expectations to get some difference equations. And in the most simple case, which I have just mentioned, that we remember the first and last step, and assume that the first step is giving x1 is equal to 1, then we get a very simple difference equation for xn plus 1, the expectation of xn plus 1, namely it's 2p minus 1/2 times expectation of xn plus 1. So this is a difference equation of first order with constant coefficients. And one knows quite well what the result is. It's written down here, and then we can calculate in detail the expectation. And similarly, one can calculate the variance. But this is already a second order difference equation, and we have to deal with covariances and so on. And unfortunately, the order of the difference equations increase with moments. The higher the moments, the higher the order is, and the size of the memory. So we had to give up very early to calculate explicitly the moments. And now I come to a very different topic. Assume that P is less than 3 over 4. So we are in the diffusive case. So where we can expect that random walk is passing zeros again and again. And the question is, for example, what do you know about the stopping time for passing a zero? So tau naught is the smallest index j such that Sj is equal to 0. And also one could ask, what are the number of zeros between 1 and n? And quite nice result going back to Bertrand. He showed that the probability that the stopping time is bigger than n, so we have to wait more than n steps until a zero comes up. This is asymptotically to a constant times some n power. And if you look at that n power, if p is equal to 0, so to say, it's n to the minus 3 over 2. So if you calculate the expectation, you have to sum n to the 3 over 2 up, and this is possible, it is finite. If p is 1 over 4, then you have n to the minus 1. And if you sum up the sum 1 over n, this is divergent. So the expectation of tie naught is finite if and only if p is less than 1 over 4. So you have many changes of the sign of the previous random variables. Then the sign changes occur more often. And what is astonishing then, that the number of zeros between 0 and n divided by square root of n converges to a non-generated random variable. The distribution of tau naught is always heavy-tailed, and the expectation, as we saw, is only finite if p is less than 1 over 4. And the Cn divided by square root of n behaves nicely for all p, is different from a classical Markov chain, for example, with finite state space, where the order of square root of n is correct if and only if the stopping time naught has a tail like n to the 1 over square root of n. So it's quite a special situation here. The basis for the proof is a Brownian embedding that helps here nicely. If you stop at a 0 and stop at the case 0, you start again, and mkn is a and k times sn plus k. A and k was a normalizing constant, so that you get multiplying it with s to a martingale. This is a binary splitting martingale, giving sk is equal to 0. And then one can construct random variables tkn such that mkn and the Brownian motion at the position tkn have the same law. And this helps, so to say, from the knowledge of very deep knowledge we have about Brownian motion to understand what's going on. This is just a rough idea how one can prove that. We could also ask, can we say anything about first passage times of a high level? Say tau n is a minimum of all k, such that sk is greater or equal to n. Well, because we have step size 1, it's minimum of all k that sk is equal to 1. The first observation is that the stopping times are not proper random variables in the super diffuses case, naturally, because, for example, if tau would be finite almost surely for subsequence nk, then as tau nk tends to infinity, s tau nk divided by tau nk to the 2p minus 1. Remember, Sn divided by n to the 2p minus 1 converges to L. As S tau nk, this is nk, because tau nk was just defined to be at position nk. So this converges then to L, but L is not a positive random variable, but in this limit, L should be positive, because nk divided by the stopping time, these are two positive quantities, so it should be positive. So there's a contradiction. Hence, tau nk is infinite for all k greater than k naught on a set of positive measure, and that implies that tau n is infinite for a large n on this set. So this is not a stopping time. In a diffusive case, we get at least some lower bounds for tau n. For example, if p is less than 3 over 4, the lim inf tau n divided by n squared log n is greater or equal to 3 minus 4 over 2. And in the critical case, we can also give a limit. Okay, this is connecting also to some questions in the new theory. Let's keep that. For the case, super diffusive case, we can consider the case where sk in absolute values reaches n, and there tau n behaves essentially like n times to the power 1 over 2p minus 1 times some constant. This follows directly from the limit theorems we have proved earlier. What can we say about distributional conversions of tau n? So tau n is the time until the random walks increases over the point n. For p less than 3 over 4, we can give a limit by using embedding in a Brownian motion by a special distribution of t times the Brownian motion and its maximum of t between 0 and 1. And so a similar result can be proven for p is equal to 3 over 4. So essentially, the stopping time up to reaching the level of n is of order n squared. So this is what we got. And we can also do this for different memories. For example, if you think only of the last point you remember, then you get also a distribution limit theorem with some distribution which is in 1 over the phi 1 squared distribution. It's the S 1/2 distribution. Now, in the remaining time, there's not much time left, I would like to talk about a random walk where stops are admitted. So x1 is -1, +1, or 0. With the 3 probabilities written down. And xn plus 1 is again constructed from the previous axis, or is equal to 0 in some cases, and from the previous axis such that one of the axes is chosen randomly, uniformly randomly from between the first n random variable. This means that the random walk stops from time to time and then goes on with a slight different dynamic. Svante Jansen was saying when we were talking to him, I think you know him, oh, there are many zeros. Yeah, there are many zeros. So the number of non-zeros is of order n to the 1 minus r, essentially. It's a little bit more precise, that it converges almost surely to some random y, which has certain moments which where we can calculate the expectation of the variance. If we want to discuss the limit distribution for Sn, we are in a quite different situation because if we want to have a central limit theorem, we have to normalize not by n at first hand, but by the number of non-zero contributions, because only these terms where there's no zero coming, something is going on. So we need n and star to deal with. So if we consider a random walk where we have y1 is equal to 0 or 1 with probability r or 1 minus r, and the next random variables, if we have defined the first n, we choose again randomly one of the first random variables with probability 1 minus r, or we put in a 0 with probability r. So this is a process which defines zeros and non-zeros in such a process. And then we would like to know more about the sum of the y's. And then there comes up a Mittag-Leffler distribution, Mn alpha, which has a moment generating function as written down at the last line in this screen. And then the probability that Tn divided to n minus r less or equal to x converges to such a Mittag-Leffler distribution. Well, we admit also that the first random variable is equal to 0. This gives this additional term r times delta naught of x. And one can also deal with different memories again. I will skip this. Now there's a result by Heidi again. Sn divided by square root of n star is asymptotically normal. And furthermore, Sn and n star are independent. So we come, if we consider the distribution of Sn divided square root of n star, we can calculate this with the help of a multiplicative convolution of the two distributions, the normal distribution and the distribution of n star. And then we get Sn divided by square root of n minus r as equal to x converges to this distribution is probability 1 minus r plus r times delta naught of x. And Sn divided by n minus r converges to 0 almost surely. And there's also a result in the non-diffusive case. The diffusive case is a little bit different than before. It's 3 over 4 times 1 minus r. And the non-diffusive case in the right-hand side of the corresponding interval.
And what about, please, sorry, the previous
What
slide.
about?
What about the case where P equals to 3/4 times 1 minus R?
You can also deal with that. I have not really, we have so many specific results, so I skipped one.
Okay.
Let us come back to the restricted memory, for example, and this process where you have zeros. What happens if we remember only the last L steps or L plus 1 steps? So if L is equal to 0, you remember just the last step. And then the process may stop completely, because if the step n is equal to 0, then the step n plus 1 is either the end step, which is 0, or it is 0. In any case, it's 0. So the process stops completely. After some time, tau L is, and we get a total sum of our random variables S. So S tau L, so to say. So what do we know about these quantities? If L is equal to 0, then S and tau are geometric random variables with mean 1 over R or 1 minus R over R respectively. If L is equal to 1, so we remember 2 points, n minus 1 and n, then the expectation of tau and S is as we have written down it in the second last line. And if n is equal to 2, I'm still able to calculate the expectation of tau, but not of S, and all the other quantities I am not able to get a hand on. It gets more and more complicated. So there's also still an open problem. We cannot do anything with it. Let me just finish with some of the literature which is related to the talk. These are some of the papers I have mentioned during the talk. Here are essentially the papers I have with Alan Good, and some more of the results I have mentioned. And thank you very much for your attention, and I'm happy to answer some more questions if I'm able to.
Thank you, Lee, for this nice talk and for these nice open questions. if there are some questions. I start by my question. If the elephant had imperfect memory or noise memory, how would that change the model?
Sorry, if
the elephant had imperfect memory or noise memory, he cannot remember exactly the step XK, for example. There are some noise.
Yeah.
How would that change the model? Can I think about this model, about this problem?
Yeah. If the noise is independent, the question is what is the next step depending on only on the axis or also on x plus epsilon? If epsilon is a noise,
yes, epsilon
as
is a
usually in
noise.
statistics, then things become more complicated. If you have each time additional noise which you don't use for the future, then things are simply because you just have independent, normal distributed random variable. But the other case is different because then you have each time different random variables. Yeah, that I have no idea what happens. Maybe that is also interesting. Yeah, because this is. If you have a statistical thinking, this would be typical that you don't observe the axis but some axis plus a noise. There are also questions, statistics, for example, if you have such data, how can you estimate P or P and R in the last case, in the random walk stops?
Okay.
This is a relative complicated, statistically complicated question because you can give an estimator, but the speed of conversions of this estimator is very low. So it's a logarithmic order.
Okay. So the origin of the elephant random walk, well, this problem was introduced by two physicians, I think.
Yeah.
Have you some motivation from physics of this model of the elephant random walk?
I think they have the question came up from people in physics, and the papers were also published in a physics journal. But I didn't see really what their motivation was.
Okay.
Whether I cannot say anything about that.
Okay. Cyril, can you ask your question, please? Cyril Bondelier.
Yes.
Yes,
so,
please.
is it the case that the maximal height of the process was analyzed and what it is for p equals 3/4?
No. The extreme, no, we haven't done that. And I have not seen anything about this.
And there are not even some conjectures or whatever?
I'm not so sure because you see, all the results are different from the classical random walk,
Yes, this is
where
why
the
it's
maximum was analyzed
funny.
quite well. Yeah. No.
And
I just came across this question when I was this afternoon looking through the talk again. I said, well, no, I don't know anything about that.
But sorry,
yes,
Cyril. I think it is a very nice question, the problem of the height of the elephant random walk.
Yeah.
And is there any other non-trivial parameters which were ever analyzed?
What do you think is a non-trivial parameter?
Or for example, it could be the area below the lattice path.
No. No,
You
not
know,
I'm aware.
for in the classical Brownian world, it is area distribution. So here
Yeah.
it is also natural questions to ask what would be the area below the absolute value of the process, if you want.
Yeah. No, I cannot immediately answer this question. Yeah.
Mhm. And when you mention the limit of Mn going to infinity, is there any conjecture on some transition phases for some specific value of Mn?
Yeah, that's an interesting question. I uh, if you look on uh, why are there different cases coming up? This depends, if you look through the results, depends on the influence of the first random variables. Um, and I think uh, these different phases come up if Mn is very large, or maybe even Mn divided by n tends to 1. But I'm not really sure.
For the when the elephant remember only the first Mn steps, and Mn increase to plus infinity such that Mn divided by n converges to C, there are no phase transition with respect to C. There are phase transition only with respect to P, to the memory parameter P.
Yes, that's right. Yeah. I thought his question was on the other side, so remembering the last steps.
Okay.
Whether depending on Mn, the behavior of Mn, if M is relatively small, there will be a normal distribution, Mn divided by n
Yes,
to
because
0.
then it's you have a Markov chain.
From when on do we get different phases? So supercritical, critical, and diffusive cases. I don't know.
Okay, so a lot of work to do. Okay.
I believe it will be maybe only for the case that Mn divided by n tends to 1, but I'm not sure.
If you could go to the previous slide, please. The last slide. Okay.
This one?
Okay, this one. In the case where L equal 3, for example, if we have 3 successive steps equals 0, then the walk stops. Okay.
Yeah.
Okay. But the probability that we have 3 0 steps is non equal to 0. It's different from 0. Then I think using the large law of numbers, strong law of numbers, we are sure that it arrives a step that we can have 3 0 steps. Then in this time, then the walk stop.
Yeah, in all these finite, so if for all finite L, the walk will stop sometime. The question is, what is the waiting time, and what is the total sum of S tau L? And this is open question.
Okay. Are there alternative?
At least you have a moment.
Okay. Are there alternative approaches, non-martingale, that could lead to similar asymptotic results? Here in your talk, you present as essential tool the martingale and the quadratic variation, the convergence of martingale. Are there other tools other than martingales able to give the same asymptotic result?
The only I don't know. I'm not sure whether I understood you properly. In the when you remember the last M steps, then this is a Markov process of order M, and so you can essentially reduce that to.
My question is about for example, the classical elephant random walk. For the study of the classical elephant random walk, we uses only martingales as tools. Or
mainly,
okay. Yeah. Are there other approaches other than martingale that give the same asymptotic result? For
I'm
example,
not aware. Maybe one could do something with Brownian embedding, but I never followed it because this is also tricky. Yeah. It's just in the context of the zeros what Bertrand does for this. But otherwise, it's the only thing I saw martingales,
okay.
which is a very nice tool.
Some other questions? If we consider the classical elephant random walk, and we suppose that elephant does not moves every step, that the time between two moves is exponential distributed random variable, for example. Okay, after a time with length exponential with parameter 1, he moves plus or minus 1. Can us obtain some results for this model? We obtain a continuous process in this case.
Okay. So you have a long waiting time, or you have an exponential waiting time.
Yes.
And then the elephant moves again.
Yes, moves according to the same scale. You remember one previous step.
I had not seen that. Okay. Can you send me a reference?
I have no reference, just a question. Okay.
Oh, the question. I thought you have a result about that. Yeah. No.
Do similar phase. Okay, sorry. Yes, yes, Eli.
No, it's okay. This is related to the last question. Yeah. Yeah. Yes. It was the last slide. Yeah.
Yes. Do similar phase transition occur in other reinforced or memory-dependent stochastic processes? Are there other memory-dependent stochastic processes where we observe the same phase transition or analog phase transitions?
I cannot. At the moment, I cannot. I'm sure there is something, but I cannot answer this question right out of the head.
Okay, thank you. Thank you. Other questions? If not, we have to thank again Professor. Yes, I think that there are a question in the chat. Sorry. Thank you for the talk. We have to thank again Professor Ulrich Stadtmüller for this nice talk and see you next week. Thank you.